So here's a high-level overview of the research that I'll be presenting today. First of all, we try to understand what are trade-offs when you take MapReduce to this kind of a highly distributed environment. And in particular, we'll compare few different ways to execute MapReduce and see what the issues are and where the trade-offs lie. And then secondly, I'll talk about how do we then go ahead and optimize execution of MapReduce in such an environment. In particular, how do we determine where to place data, where to execute tasks, etc. So in order to understand the trade-offs, we'll again remind ourselves of the MapReduce workflow model. So in this case, now you may have distributed input data sources. So instead of having a single data source, you may have the data distributed geographically. So you want to push this data to the individual mappers, carry out the map operation, and then shuffle the data to the reducers, which will generate a final output. So now you may have bottlenecks in different parts of your workflow. The data push itself may be costly depending on where the data is located and where compute resources are. Similarly, this shuffle operation, which may reduce to a all-to-all communication, may be costly, and then finally, even your output data generation may be costly. So we try to understand where the trade-offs are and where the bottlenecks are. So to do that, we basically take a simple model. Here we assume that we have two different data sources, one located in US and one in Europe, and we have corresponding clusters close to these data sources, again, one in US and one in EU. So one way to execute your MapReduce on all this data is to basically do what you may end up doing today. Send all the data to one site, carry out MapReduce like you would typically do on a local cluster, and then get the output. So this would mean pushing the data from the US source to this US cluster, pushing it from the EU source, which may be much slower, carrying out the MapReduce computation, and then getting the output. Another possibility is to actually set up a global MapReduce cluster over all of these resources. So in this case, now your data may be pushed to both places, okay? And then you will carry out some sort of a high-level MapReduce job over all of these machines and get the final output. The third possibility is to carry out the computation close to the data source, and then once these partial computations are finished, then you somehow combine the results and get the final output. So we ran some experiments on MATLAB, which provides us with high geographical distribution, and looked at the results for different applications and different data inputs. So this graph shows what happens when we run word count on regular English text. Okay? In the graph, we have three different bars corresponding to the local MapReduce, which runs everything centrally, global, which just assumes everything is a single cluster, and the distributed, which runs things close to the data source first. And the different points on the x-axis correspond to the different stages of the computation. Okay, so the first bar, for example, corresponds to pushing data from the US source. This is pushing from the EU source and doing the map, reduce, etc. So here what we see is that the distributed MapReduce architecture does the best, where you are doing computation close to the data source. Then we ran word count, but this time with a random input, so that now there are many more unique keys in the data. So now what we see is that a completely different architecture, the local MapReduce, where you are running everything centrally, is actually doing the best. Now the reason for that is that in the first case, pushing the input data to the mappers was the dominant cost. But in the second case, combining the intermediate and the output result was the dominant cost. So what this is telling us is that there is no single way to actually optimize your system. It depends on, first of all, what the network topology is, and in addition, what the application characteristics are. In particular, how much input data it has compared to how much intermediate or output data it has. Now we also executed some experiments on Amazon EC2 across multiple clusters, and we basically see the same kind of results. So what do we learn from these experiments? First of all, we see that we would like to have MapReduce be made more topology aware. So there is some topology awareness currently built into MapReduce where it's aware of things such as there are racks within a data center, etc. But in a highly distributed environment, you want to provide it with more topology information, such as what computation is being carried on locally in the specific data center, etc. Secondly, application characteristics also determine what would be the optimal way to execute the MapReduce. In particular, if you have high aggregation, which means that the size of intermediate data is much smaller than your input data, then you should try to optimize the initial push operation. On the other hand, if the intermediate data is much larger, then you may want to optimize the shuffle operation. And then finally, you want to make globally end-to-end optimally decisions instead of just trying to optimize some phases in the execution. As we'll see later, if you just try to optimize, say, the push operation or just the shuffle operation, that may actually not give you the benefit because there is dependency across the different phases of the computation. So in order to optimize MapReduce execution in such an environment, we are building a framework using which we can model any MapReduce execution. And we have also developed an optimizer which basically provides us with an optimal plan, which tells us where should you place the data and where you should execute the different MapReduce tasks. Okay. And in particular, this optimizer is first of all topology aware. So it takes into account the underlying network topology as well as the compute capacity of the different nodes in the system. In addition, it's application aware, so it takes into account what the data aggregation characteristics of the application are. And then finally, it does a globally optimal decisions. It makes globally optimal decisions instead of doing decisions only at the local level. And we have made some changes to Hadoop 1.0.1 in order to implement some of the model outputs, the execution plans that the model provides us. So what is the model itself? It basically treats the whole MapReduce execution as a tripartite graph. Okay. So in this graph, you have a set of nodes which are the data sources, and again these may be geographically distributed. Then you have a set of nodes which correspond to the different clusters or data centers where you will be running your mappers. And then finally, you have a set of nodes which are the reducers. And the links between these nodes correspond to the network links which will carry the data. So the model takes in various parameters which correspond to the underlying topology of the network. So it takes in parameters such as what are the link bandwidths of the different links in your system, what are the node capacities in terms of the computation rates, etc. In addition, it also takes into account the aggregation behavior of the application. We capture that using a parameter which I refer to as alpha. So this is simply the ratio of the intermediate data to the input data. So if alpha is small, that means that a lot of the input data is being aggregated together. Okay, so this would be an example of word count where many words appear many times, so you get a lot of aggregation. On the other hand, some applications actually end up expanding the data. And an example of that is building the inverted index that is used for driving the web search engines. So you get a lot of raw data, but then you build additional structures around it and index the data. So given these parameters, the model will generate an execution plan which basically will tell for each source where to push the data and for each mapper where to send its intermediate data, which the user should execute on which intermediate data. So here's some math, and we don't necessarily have to go into the details of these equations. What these constraints are basically telling us is that all the data that is being generated by the sources should eventually be processed. Okay. That's what the first constraint is telling us. The second constraint is telling us that each key should be reduced at a single reducer. So this is the requirement that we had talked about earlier, that each intermediate key should be processed by a single reducer. Okay. So these are the basic constraints we need. And then what the optimizer does is, it simply minimizes that total end-to-end runtime execution. And how does it determine the runtime? It basically uses these model parameters that we have provided and the execution plan, and it determines the best execution plan so that you minimize the amount of time that the whole system will take to run.